everyone. This is a San Francisco Big Analytics. My name is Chester Chen. I'm one of the organizers for this meetup. San Francisco Big Analytics has been, operating, roughly about once a month or sometimes twice a month events for the last 7-8 years. So we're, about 15,000, more members. Since pandemic, we've been moving online mostly. So today we have a very special, two colleagues from NVIDIA, and they are the experts in the machine learning, deep learning, and XGBoost and traditional machine learning. So two speakers are talking about the similar type of topic and on the Federated XGBoost. So the first speaker, Ron is the principal engineer at NVIDIA. He has been developing machine learning related, doing a lot of research in machine learning related work from all levels. And so he's true expert from the CUDA level all the way to the application levels, So the recent years, he had been contributing both the Spark and also the XGBoost. He's an active contributor to the XGBoost code base. So our second speaker, and Ziyue is senior data scientist working on the deep learning, traditional machine learning on the federated learning side. So so both of them are going to cover the similar topic, but it's a different method, different approach. So first part is going to be given by Ron. He's talking about histogram-based federated XGBoost. With that, back to you, Ron. Please take over.
All right, thanks for the introduction, Chester. Yeah, like Chester mentioned, today we're gonna have cover Federated XGBoost from two angles. First, I'll just go over XGBoost itself briefly, just in case you're not familiar with it or haven't used it in a while, and then I'll cover kind of the approach we've taken to modify XGBoost itself to support federated learning. And Ziyue will cover the second half to talk more about sort of a algorithmic change to make it possible to do federated learning without actually changing the XGBoost code base. All right, I assume most of you probably have already heard about XGBoost, otherwise you probably wouldn't be in this meetup. So I'm just gonna go through this pretty quickly. If you have questions, we can go over them later on. So what is XGBoost? It's on a high level, it's a gradient boosted sort of decision tree library. It's pretty popular on Kaggle computations. I think there was some statistic, maybe this is like a few years old. There's like a large percentage of the Kaggle computations were actually won by XGBoost. So it's very good for if you have tabular data, right? If you have things like CSV files, or you have a SQL database table you want to train some model on, it's very good for that kind of training data. So it supports the basic machine learning models like classification, regression. There's some work done on ranking. I think Yahoo actually used it to do some search ranking back in the day. I don't know if they're still using it. I think maybe more recently, we've also added like survival analysis to the library. So it has all these, it supports dense and sparse features. It's maintained by DMLC. I guess currently there's sort of the active contributors are actually mostly from NVIDIA, but we do have outside contributions as well. Yeah, I guess since we all work for NVIDIA, I need to mention that the GPU support is actually pretty good on XGBoost. I can see pretty big speed up if you have GPU available. So what is a decision tree? So on the simple level, it's really just sort of a binary tree, right? I don't know what is actually predicting here. I think it's predicting maybe some house value. So it depends, asks like, what's your salary? And then, oh, it's not predicting, maybe it's predicting the salary. So basically, at each node level, you have a decision to make. You answer yes, it goes one way. You answer no, it goes the other way. And finally, you reach the leaves, and the leaves will have some kind of weight associated with them. So once you reach the leaf, it will give you the kind of the final output for your prediction. So the way XGBoost works is we actually sort of chain these decision trees together, so it becomes a kind of a forest. So as you go through each tree, you reach the leaves, you get the weight. You go through all the trees, you get the weights from each tree, and you add them together. That's your final prediction for your input. Yeah, so just go into a little bit of the underlying math, right? It's really just it's similar to other machine learning problems. You're trying to optimize, minimize the loss function. So here you have the first term is basically the per sample loss, right? You compare the output from your prediction versus the actual label, and then there's a so the regularization term. So we're trying to analyze the number of leaves and also the leaf value. So you don't want to have very big trees with a lot of leaves and very heavy weights to avoid overfitting. Yeah, so here's just some more math. So in order to optimize this loss function, we take sort of the Taylor expansion together. First and second order expansion of the loss function. And then if you do some sort of algebra, you can figure out the explicit solution for the weight values given the gradient and the Hessian of the loss function. So originally the algorithm was sort of a greedy algorithm, right? You just take one tree and one node at a time, and you go through all the samples, all the features, and then you compute the loss reduction, right? Then you find the feature that gave you the biggest loss reduction as a node, and then you sort of greedily build up your tree. You can imagine this actually, if you have a lot of features and your features have a lot of distinct values, it becomes very expensive to do this. So improvement on that is this histogram-based algorithm. So that's basically the kind of the algorithm used for distributed training and GPU-based approach. So it's sort of the similar idea based on as the greedy algorithm, but instead of working with individual feature values, you first sort of quantize the feature that you find you sort of divide the feature values into different bins, and then more precisely different into quantiles, and then you sort of convert the features into these bin numbers. So that way you can, even if you have a very large range of features, you can limit the number of bins, right? Typically, I think the default is 256. So even if you have a very large range of values, you can sort of quantize the features, makes them more manageable. So that's kind of the pre-processing step. So once you convert into bin numbers, that's the only features you deal with. And then, like we mentioned before, you compute the first and second order derivatives of the loss function. And then there you also create histograms of the gradients. And then you basically doing the same loop for each feature and each cut. You try to compute the loss reduction, and then find the split with the biggest loss reduction. So it's a kind of similar algorithm, but you're sort of bounded by the number of bins. So it's not, so you can deal with much larger data sets. So since we're going into federated learning, so first we need to understand how the distributed learning setup works, right? So in a distributed learning environment, you typically split the data between your different workers. Let's say if you have some kind of a Spark cluster, a Dask cluster, you might have a dozen server nodes. Each node will be responsible for a subsection of the data. Typically, it's kind of you can think of it like a horizontal split. Maybe you have 10 million rows. Each worker take care of like 1 million rows. So the only difference between kind of the single node histogram method is when we are doing the pre-processing, right? Once we find the quantiles, we have to aggregate the quantiles across all the workers, right? So because each worker only has visibility into your own slice of data, so we have to combine them into a global quantiles. So that code is actually, you can imagine, it's actually pretty complicated to figure out a global quantile based on local data. So there's it's actually not a sort of exact method. There's some loss in accuracy based on my experiments. So the distributed learning results are not exactly the same as a single node results. And then when you're actually doing the tree construction, once we compute the gradient histograms, so that's a pretty straightforward additional step. We just need to sum them up across all the workers. And then the rest algorithm is exactly the same as the single node one. So now switch to federated learning. I guess kind of like the motivation for us is why do we need federated learning, right? I mean, you look at all of the real world use cases, especially you're dealing with medical data or financial data. There's a lot of privacy concerns, so you cannot really share the data with third party, or even if you have a sort of a trusted so the central party, right? Sometimes you cannot share the data at all, and there's also like laws and regulations that prevent you from doing the sharing, even if it's technically feasible. So the idea of federated learning is, can we actually train a model that take advantage of all the data each party has without actually needing to aggregate the data first? I guess federated learning is actually a pretty kind of broad concept, right? Like I think originally when Google researchers started talking about federated learning, they were actually thinking doing learning on Android phones, right, to do the keyboard prediction. So that's a very it's a very different scenario from what we're thinking about. So there you might have millions, hundreds of millions, even a billion devices. They're very low power and they have intermittent network connectivity. So that's a very different problem from what we are considering here. In our case, we assume maybe you have a handful of, say, hospitals or clinics. Hopefully they have access to some GPU accelerated compute. They have fairly fast network connections. So that's kind of our focus, at least at this stage. And then also when another sort of way to think about federated learning is, like I mentioned before, you can sort of slice the data horizontally or vertically, right? Horizontally means each worker would have different rows of the sort of the table, right? Vertical just means if each worker would have different columns of you can think of it like a SQL table. So our initial focus was on the horizontal one. So that feature is launched, is in the latest XGBoost release. We're currently working on the vertical federated learning. It's almost there, but it's not in the release yet. Yeah, so that kind of goes back to the sort of histogram-based distributed learning, right? So the kind of this first approach is like can we actually extend the distributed learning to work in the federated environment? the idea is the kind of architecture is very similar, but we need to be able to do this training across a wide area network, right? It's not going to be the whole thing. It's not going to be in the data center. Another constraint is it's pretty very hard to sort of open up firewalls between the participants, right? If you imagine if you're a hospital, you're holding your data, maybe it's okay to connect to some cloud service, but it's a lot harder to actually connect to another hospital directly. So we have this constraint, like not to have peer-to-peer connections. So that's kind of the dictates what the basic architecture is, right? So like I mentioned, in a distributed environment, your clients probably would have direct connections between them, and they all sit in a data center, so you can assume they have very fast network connections. But in a federated environment, we sort of have to proxy through a third party. So this third party is, so in our design, we run a gRPC server. The gRPC is a remote procedure library, I think originally developed by Google. So it provides remote procedure calls. Optionally, you can add SSL to make it more secure. Yeah, so we basically sort of extended the distributed training mechanism, right? The distributed training mechanism basically just use sort of MPI primitives that's like all reduce, all gather, and broadcast. So we implemented these methods in the gRPC server, and the federated client would connect to the server, make these calls. So to them, to the algorithm itself, right, it's actually transparent because you're making all reduced calls before, and you're still making all reduced calls, but it's just the underlying transfer mechanism is different. Yeah, so if you look at the kind of the code in XGBoost, so we actually did some refactoring to so the tree construction would instead of calling the sort of underlying or reduce directly, we introduce this communicator interface. So we have the different implementations. The Rabbit communicator is the default implementation for when you are running inside the cluster. And then we added this federated communicator that's basically proxy through gRPC through this central server. And on the GPU side, there's also a sort of by default, it uses NVIDIA's NICO library for GPU to GPU communication. In the federated environment, we have this adapter basically copy the data from GPU to system memory, and then forward on to the federated communicator. Yeah. So so the design is actually fairly pretty simple, and then I think the nice thing is we don't have to make any algorithm changes to the tree construction. Here I'm just going to show you some sample code. This is just the first step. We have some convenience method to start the federated server. You give it a port number, and the word size is just the number of workers it anticipating. And then when you're in the client code, you basically launch these workers. It's the same port number and word size, and the rank is sort of the index of the worker. And then this method is mostly the same as if you're doing like a single node training. The only difference is you sort of wrap the training code in this communicator context. You tell it to use a federated communicator and the server address, word size, rank. So this is just a very simple sort of demo code you can run on your laptop. It just kind of fork out different processes to simulate the federated environment. Yeah, so we have this simple demo in the XGBoost repo. We also have NVFlare integration. I think Ziyue is going to touch more about. And then we have more extensive examples in the NVFlare repo. So what's next? Like I mentioned, we've been working on vertical federated learning. It's kind of a similar idea, like we want to extend the current distributed algorithms to support both sort of feature parallelism in a distributed setting, and also sort of vertical federated learning. So the work is mostly done. We're still trying to kind of verify the behavior in all the cases, and we'll add more examples and the documentation for the next release. But beyond that, so right now in a distributed environment, you're sharing sort of these gradients, and you're sharing like when you do the quantile feature, trying to come up with the quantile, you're sort of share the bin boundaries. So there's still some, in some cases that might be okay, but in other cases, maybe you're still leaking too much information, right? So so we need to consider adding more sort of privacy features. You can do that through encryption, or there are some algorithm to you can share some secrets between the workers, and then you can compute maybe the quantiles without actually revealing the underlying data, things like that nature. So those are kind of in the future plans we haven't started working on. I think that's all I have. Jesse, do we want to take questions now?
Yeah, let's take a few questions. I think that we got a few. So the first question is what are the applications of this? Any use cases where it helps? Is similar to running scikit-learn like on Ray? That's one question.
Yeah. So so I guess like let's go back to this motivation, right? If you're talking about sort of XGBoost in general, right? It's a much more sort of industrial strength gradient boosting system. I know there's other implementations of gradient boosting, a decision tree, but usually, I think if you just look at the results from category computations, is definitely XGBoost has an advantage over other libraries when it comes to decision trees. In terms of kind of a federated learning, right? Like I mentioned, this I think especially in a sort of medical environment, right? Let's say if you have patients, they have test results or you have maybe some DNA sequencing tests, or all these things. I think it's very hard to have this central data repository that aggregates all the information for a given patient, right? And then but if you want to train a machine learning model for these patients, so without federated learning, you're sort of limited by what the data you have at each individual hospital or clinic, right? But if you can combine all this data across these different entities, you can potentially train a much better model, right? Imagine if you, in addition to your lab test results, you also have the DNA sequence data and maybe the doctor's diagnosis in the hospital. All these things, if you can combine together, you can train a model to predict patient outcome, or you can do like clinical trials, all these things. So that's like one environment is very, very useful. Also for financial data, right? Like if you might have your checking account in one bank, and you have your loan in another bank, right? And also it's very hard for these different banks to share data even on the same customer. So if you want to predict, say, credit default risk, whatever, you might want to combine all this data for each customer, but you can't really aggregate the data to train your model, right? So in that case, you also need this federated learning approach to train a sort of a joint model without sharing the data first. Does that answer the question?
I hope it does.
Yeah.
Sorry, go ahead. Srinivas, if you want to say something.
No, yeah, thank you. It helps us, at least on healthcare and the finance-based use cases. I think it makes sense. My only question is, see, XGBoost is one type of algorithm, right? So there could be several types of other algorithms that we can apply that we can apply in the arena of federated learning. Is there a reason why you are saying the XGBoost in these use cases for federated learning? Yes, we can apply. I think it makes sense. But are you saying that there is not maturity enough in the industry where you can apply other algorithms similar to XGBoost in the federated learning space? Are you saying that?
Are you talking about the decision trees, or are you talking about the other, like, for example, deep learning?
It could be learning. It could be any other. There could be several algorithms that I'm assuming that.
Yeah. So I think we should talk more about the NVFlare, which is our library to support federated learning. So they actually cover deep learning. They also have support for XGBoost. But the main focus there is actually on deep learning. So I guess it's a question to answer your question is that in order to support federated learning, like you need to either to modify the machine learning library itself, right? In this case, we're doing here, or you have to do what NVFlare is doing for like deep learning. You have to do like a federated average of the gradients, things like that. So it's not for most machine learning libraries, it's not you cannot do federated learning out of the box. So you either have to modify the library itself, or you have to use like NVFlare to drive it.
So I can address that question. For the he was asking the are there any examples for this case? I just in the chat I posted a GitHub repo. But in terms of the general question, whether the other machine learning libraries, actually our second speaker Ziyue has developed both deep learning as well as the traditional machine learning that in our most recent release in NVFlare. So that includes the linear model, the logistic regressions, classifications like k-means, support vector machines, and of course there's XGBoost, and also there's a random forest from the XGBoost. So there's quite a variety of the both deep learning as well as the traditional machine learning. You can go to the examples on the GitHub repo to find more, more examples. Let me move on to the next few questions. There's a question, any specific dependencies on NGPU or CUDA? I'm not quite sure I understand this question.
Yeah, so like I mentioned, XGBoost has GPU support, but it's not required. You can still do CPU-based algorithms if you don't have access to GPU. I think just if you have a large data set, it's just the speed is very, very different. Even if you have many cores CPU compared to even just kind of a regular gaming GPU, the speed difference is pretty substantial. So you just kind of make it a little bit faster if you have access to GPU, but it's not required.
Okay, next question is, has there been any benchmarking done compared to results of federated XGBoost with a federated neural net on the same learning task?
I think, yeah, Ziyue might have some numbers. I don't think we've compared in terms of kind of learning accuracy, right? Well, I guess like another way to think about this, so you're basically asking comparing XGBoost versus deep learning, because in this histogram-based approach, it's basically lossless, right? The federated learning training is effectively the same as distributed learning with XGBoost. So there's no sort of accuracy loss compared to distributed learning. But then I guess on the deep learning side, I don't know all the details, but it's possible you might lose some accuracy, right, if you're doing federated averaging. But it's
that was my question. Yeah, sorry, that was my question. Is that the aggregation step that we see happening for neural networks or like those kinds of parameterized models, right? Even linear models. There's been obviously some research put out that they have their limitations, right? And I was kind of curious. I kind of missed when you were talking about the lead up to the XGBoost and how you guys actually fit it into the federated learning framework. But yeah, any kind of findings comparing those two on the same learning task would be really cool.
Yeah, I don't know if Ziyu has any information regarding that. So for our side, like for this part of the work, right, we are basically just trying to replicate the distributed XGBoost. So in terms of learning performance is identical, but in terms of sort of performance, in terms of training speed performance, right? There's that depends on your sort of network and your setup. Yeah, probably I think wait until Ziyu talks about the kind of the tree-based approach. See if that answers your question.
There's two more questions, and I just want to quickly wrap that up. So one question is from Rahit, says, can you explain the histogram-based XGBoost in a FL setting using simple example is 2 clients and 2 features?
Yeah, so let me see. Yeah, so I don't know if we can do that. Yeah, so like I said, I think the distributed training and federated learning is actually from a sort of algorithm point of view, it's the same, right? So in a single node, we try to find the quantiles of each feature. In the distributed learning case, we need to extend the sort of local quantiles and sort of aggregate them together to find the sort of the global quantiles of each feature. So there's an aggregation step there involved. But once you do that, you basically convert all the features into these bin numbers, right? So basically, your floating point number is converted to this, you know, for example, 256 bins, and then when you're constructing the tree. So once you construct the tree, then you can calculate the loss, right? Then you can calculate the first order, second order derivatives of the loss. The only difference in the distributed environment is your loss is only each worker, the loss only for the number of rows you have locally, right? So you need to sum them up to get the sort of the global sum of the gradients, and then from there it's really just a loop for each feature, for each cut, and try to compute the loss reduction and find the best one. So in the federated environment, this algorithm is actually exactly the same. We sort of basically took out the underlying logic. So instead of doing our reduce peer-to-peer through MPI or NICO, we fire off a gRPC request, and the gRPC servers will aggregate them together and send the response back. So this is sort of transparent to the algorithm. In terms of the actual details, I don't have enough time to go into that. But if you search for XGBoost, NVIDIA actually has a developer blog post, which goes into a lot of detail talking about the basic tree construction algorithm, and also talk about how they use GPU. So that'd be a useful reference for this.
Okay, so I think the last question, and this is actually the original first question, and was asking credit line. I wasn't quite sure what this means. Is basically, are you saying that we're missing the credit reference to the original author or something? I'm not quite sure.
The example Rong showed is for the credit line determination for the decision tree example.
Oh, I see.
Oh, okay.
Yeah, 35K, 50K. Those.
Yeah. I think it's copied from somewhere.
Yeah, that's determining the credit line.
Okay, it's credit line. Okay.
Line. Yeah.
Okay. All right. With that, we're gonna invite the second speaker, Ziyu. And as I mentioned earlier, Ziyu is our senior data scientist. I've been working on all sort of applications, deep learning and medical imaging, and particularly on the federal learning pieces with NVFlare. So he's going to talk about the same topic, but a different approach. Go ahead, Ziyu.
Okay, great. Thank you, Chester, for the introduction. For my part, I'll mainly talk about the same topic, the Federated XGBoost via NVFlare, but it's a tree-based method. So before we go to all the details, maybe let me first add some more information about the federated learning. The federated learning really is starts in the deep learning domain, where people wants to do some collaborative training, but without the need of sharing the actual data. So naturally, the idea will come to, well, following the same idea as distributed learning, where the different workers process different data, and then the resulting gradients got synced together, and then for that will be applied to update the model. That is what we can call as data parallel, which is widely used for a local centralized training. If you have a lot of data, you can use the data parallelism to process them in separately and then sync them together. But in reality, if we want to apply the same idea using different machines or different silos, this becomes a very challenging thing to do for deep learning, because well, for deep learning we have just too many optimization steps to do. Say we have for one epoch, we have say 1,000 batches, and then if we want to execute for 100 epochs, then essentially we have 100,000 steps that are needed to collect information. Then if we use the same idea as the data parallelism, then which means we're gonna need 100,000 communication steps from each client to the server. And that communication cost is prohibitive and unrealistic for deep learning. And that is why in deep learning domain we later have this idea called federated learning. Federated learning compared with basic distributed learning, meaning that instead of syncing the gradients every single step, now what we do is we just sync them every few epochs. So instead of 100,000 sync over all the communications, now we only need, say, 100 at most if we sync every single epoch. And then maybe in some realistic settings, the communication can be even lower, like we sync every 2 epochs, local epochs, or 3 local epochs to further reduce the communication cost. So really, the invention of federated learning is to, the main goal, there are 2 main goals. One is to do the training together collaboratively without the need of sharing the actual data. And the second is to avoid the prohibitive communication cost. And that is what is happening in the deep learning domain. And as you can see, the distributed learning and federated learning has a pretty obvious gap between from each other. But now let's move on to XGBoost, or we can say the traditional machine learning methods. For this set of learning methods, actually the boundary between distributed learning and federated learning becomes a lot more fuzzier. And as Ron just presented, in histogram-based case, these 2 terms can be equivalent to each other, where we just convert naturally the distributed learning to a federated learning scenario by modifying the communication layers. Now, and why is that? Because for XGBoost, the steps or optimization operations are not as many as deep learning. That's it. Like I just mentioned, for the deep learning, we can have 100,000 optimization steps, and that is too much. But for XGBoost, I guess for XGBoost model, let's say we have 100 trees. That is usually sufficient to handle any particular task. And so since it only has 100 trees, meaning we only need to repeat the process 100 times. And that's why the computation cost is affordable to make the distributed learning equivalent to the federated case and to achieve the collaboration. Well, on the other hand, the idea of syncing the local models to make a global one, and then use that particular model to start the second round of training, the same idea can be applied to the traditional machine learning methods like XGBoost. So here I will talk about two different approaches to model the XGBoost under a federated learning setting. So here is the scheme. As Ron just mentioned, for histogram-based methods, what we really do is we assign each local client to do half of the tree building process, meaning when they compute, they didn't compute the whole tree. They didn't build their own model on each site. Instead, they collect the information, that is the gradients and the hessians that will be needed to build a tree. And then those information gonna be sent to a central server, and the central server will finish the second half of the tree building process. In other words, this process is the same as distributed learning, and the model we eventually get is the same as centralized training. So we want a 100 tree model, and with this process, it will be the same. It will end up with 100 trees that will be similar, will be exactly the same as distributed learning, and will quite similar to if we collect all the data together and build the model upon those data. Now, alternatively, what we can do is we can do a tree-based learning. One way is to do a tree-based cyclic training, meaning that we built in cycle 1, we built a tree based on client 1's local data and use this as the starting point and send it to client 2. And client 2 will boost an additional tree based on client 1's tree. And then these two trees will become the model and then send to client 3, where the client 3 gonna boost an additional tree based on its own data. And then we can forward to client 4 to build his own data, boost another tree. And then again, if we only have 4 clients, it can be sent back to client 1 to start the next round. And in the end, let's say we can also have 100 trees, but each of the tree will be boosted based on each client's local data. So instead of based on the global statistics, it will be only based on part of the data. And that's in the end, we also have 100 trees, but each tree building process will be different. Now, if we really want to utilize all the information at each round, but we don't want each client to share the statistic on their own data, we only want them to share their final model, as the case for deep learning. We can also do that. How? Is that each round here, each client will construct their own tree based on their local data and say, hey, client 1, 2, 3, 4, they generate different trees based on their own local data. And those models gonna be sent to the server, and server will aggregate those trees together. And this aggregation here, what we use is just bagging them together, making them a forest, subforest. And this forest will be consisting of, say, 4 trees, will be used as the starting point for the next round of boosting, meaning that these 4 trees will be sent to each of the 4 clients. And those 4 clients will use this forest as the basis to boost the second tree in the round 2. And then in the round 2, those 4 newly added trees will be sent to the server and then bagging together as the model for the second round. Note here that now the global model consisting of 2 subforests. The first is what the older trees from the first round, and then the second is the older trees from the second round. And so instead of boosted trees, now we have a boosted forest. So this is round 2. We have a boosted forest of 2 forests, and then it's gonna be used as the baseline model to predict the next round of the third tree. And then continue. We can repeat this process for, let's say, same 100 times. But now you can see after 100 rounds, instead of 100 trees, now we have 100 subforests, and each forest gonna be consisting of several trees that's equivalent to the number of all the climbs. So this model, if we perform the same 100 rounds, it's gonna result in much more trees as compared with histogram method and as compared with the tree-based cyclic method. Okay, so yeah, this is the basic setup. As we can see, now we actually utilized 2 ideas how to handle a single decision tree. One is the boosting and the other is bagging. Essentially, these are the 2 options for combining decision trees. Boosting is to sequentially adding trees to correct the residual error, like what we do with XGBoost or any other boosting methods. And second idea is the bagging, meaning we train trees in parallel and bagging them together as a forest, such as the idea used for random forest. And with this tree-based method, actually we combine the 2 to make it the boosting of a forest. Yeah, so so that is why we call it a tree-based federated learning, rather beyond the histogram-based, because histogram-based meaning that we collect the statistics based on the histograms. But here, what the unit information that's gonna be passed from between server and clients is the forest. The federated learning really is about clients compute something locally and then send some information to the server, and then server gonna determine how those informations gonna be aggregated. So we really want to figure out what these 3 factors should be with any tasks we have in hand and any methods we are considering using. So histogram-based method essentially is the same as distributed learning. The base unit of one tree further split into 2 stages every time clients compute the histogram statistics on local data, that is the stage 1 out of the 2, and then share these intermediates for the tree computation, and then the server will be able to finish the tree construction, that is the second half of the stage. And such that we added 1 tree per federated round, and hence the resulting tree is actually virtually trained in a centralized manner with information from all clients. And keep in mind that why we can actually do that is because for XGBoost, it features limited number of communications. So what is infeasible for deep learning now is feasible for XGBoost. And on the other hand, the tree-based method works on a tree unit, starting from the global model. Each client boosts their own local tree on the local data, and then send the new tree to the server, where the new trees will be bagged together. So per federal round, we're gonna have M trees. M is the number of clients. And of course, alternative is cyclic. Each client boosts their local tree on local data and then forward to the next client for the next tree. In this case, the server actually doesn't do anything beyond just the forwarding one model to from one client to another. Actually, this can be done even without a central server, just by passing the information around all the clients. Yep. So as we just talked about, the cyclic training is just about forwarding. And forwarding the model from one client to the other and boosting starting from the model received. There is no server aggregation, and the server in this case only coordinates the model forwarding process. And binding is really about combining the two. So each client boosts a local tree based on the starting model and then send this tree to the server. Server aggregates all the submitted trees by bagging them together. One note here is that in this case, we use the bagging to combine all the trees, because bagging is the most simple and basic and obvious way of handling the tree structures. And I did some literature review, and I think there are some ongoing research or recent researchers that has been proposed to, well, combining several trees into one single tree. And that may be some more advanced techniques that we can utilize to do this server aggregation. That will be, so instead of bagging them together as a forest, now those 4 trees can be merged together to form a single tree. And if we apply that, eventually, if we do 100 rounds, and then we will have 100 trees as the result. But that's some extra effort and research to do, of course. And then the aggregate global model will be dispatched to all the clients to be used as a new starting model. So this mode is, in theory, is quite similar to what we do for deep learning, because every time deep learning, federated learning do is each client built their own local model by training, let's say 1 or 2 epochs, and those models gonna be sent to the server, and the server gonna use those models, aggregate them together. And the simple thing for deep learning is that this aggregation is simple, because deep learning we can just use the numeric average for all parameters to form this global model. But this is something much more challenging to do for a tree model. Okay, yeah, but there are something that we can also adopt it from deep learning to the tree-based federated learning. That is the weighted aggregation. So this is actually an additional factor to further consider for if we have a data size difference across clients. What we currently do as a default setting for deep learning is that if one client have a smaller number of samples than another client, then what we can do is during the global model aggregation, we can give a lower weight to those clients with fewer samples. Because we theoretically, if all the clients are in a good will and have good data, the one with more data should be considered more reliable during training. So in case we have unbalanced clients, different from, well, it's different from random forest setting where all trees are based on the same size subsets. We can adopt this idea of fed averaging aggregation with the weighted average based on data size. But the weighted average is pretty straightforward for deep learning because it can be directly injected to the global aggregation process. But for tree measures on the server side, it's not easy because remember, on the server side, when we do the aggregation, it's nothing but just bagging them together. A nicer way to do this weighted average is that we can pre-adjust the local learning rates, and such that we can give the personalized learning rate individually that is proportional to its data size. So by adding this correcting factor based on the number of samples, we can make this way equivalent to the feather averaging, weighted averaging for the deep neural network models, but for XGBoost tree submissions. So here is some experiment I did with the Higgs dataset. As we can see, this blue curve here is the centralized result, and I simulated different splits across 20 clients. We have uniform splits here as the orange curve here. We further have square splits, meaning that the number of samples of each client is proportional to a square of the client ID 1, 2, 3, 4, 5 all the way to 200. So in this case, the number 20 clients will have 400 more samples than number 1. So as we can see, under this uniform data splits, if we do a cyclic training, the performance will be a lot worse than centralized training. And if we, same thing as if on the other hand, if the data split is uniform, we do cyclic training, we can see this purple curve here. It's not as good as centralized training, but not that significantly drops. Same thing is if we use the square splits, but with bagging, we can see this green curve here. The performance is worse than centralized training if we use the uniform learning rate. But if we reinforce the weighted average, that is, we pre-corrected the learning rate on the local training, what we can get is the result that is even better than the centralized training. Well, I'm actually a bit surprised that we can actually achieve even better results than the centralized training, because my original thinking is that the best result, the best we can get is, well, we collect all the data together and build a model based upon that. But as we can observe here, if we use bagging, the tree-based methods, sometimes we can achieve even better results. And one explanation, potential reason, I think, is that for these tree-based methods, eventually the model capacity is actually bigger than the centralized XGBoost model, because thinking that the centralized model, if we do it 100 rounds, we only have 100 trees that can be that will be used to representing the task and the data. But if we use if bagging mechanism, eventually, say we have 20 clients, then eventually we have 2,000 trees. And 2,000 trees, that is, although each tree is based on 1 by 20 data, but essentially the model capacity is 20 times more than a single model built in a centralized manner. So that is one potential explanation why we can get even better result than centralized training. But yeah, that is my current postulation. I didn't do any analytic analysis to that, and yeah, this I guess this observation needs some further analysis. Okay, that is all for my part, and yeah, for the tree-based method.
Great talk. We do have two questions. One for Srinivas. He said, is there any common, let me see, just jumped. Is there any common requirements that a client and server has to follow to sync the trees? And then there's follow-up question is, what is the interface requirements between the client and server?
Client answer requirements, well, if we're talking about the library APIs, is well, you need to use the same API that is recognizable for well, for this case, since we are using the bagging, so the requirements is that we need to figure out some way to bag the submitted tree information together and send back to the local clients that local client will be able to recognize. In this case, for XGBoost library, what I did is that I collect information from the clients and then build a JSON model that will be recognizable for XGBoost library to start with. And yeah, there is some hack to do to the JSON file that make it loadable to the local clients APIs. But that is pretty much it. And yeah, that is something you need to consider when you work with a particular library. Does it have a capability to do a next round of training based on some starting point model? And does it have an API open to aggregate those information together that can be reloadable? Yeah, those are some points that need to be taken into consideration if you want to further design a federated learning version of any particular machine learning algorithm. Okay,
let me move on to the next question. What are the main pros and cons in your experience to choose between these two? I assume the cyclic and the bagging. And also, any thoughts, not from the ML performance perspective?
Yeah, so I guess for when choosing between cyclic and bagging, I think well, cyclic is a lot simpler, both from implementation perspective and from the pipeline perspective. The main consideration is if you want to have a simple pipeline, and want to have a simple model in the end that is a lot smaller than a bagging model. If you have a lot of clients, then choose cyclic. But as I just shown, cyclic, the performance can be a lot worse than the bagging case. Of course, the cyclic in cyclic case, the communication cost is a lot lower. But if you want to have a model eventually that is performed well, then bagging will be a better choice. Yeah.
So we had a follow-up question on it, just to make sure that the performance is on the training set, not on the validation set.
No, it's on the validation set. So what we do is we split this huge data set to two parts, one validation set and one training set. And then we further split this training set to different clients.
Okay. So the next question from Adam says that can tree-based federated learning method be used for both horizontal and vertical data partition?
Yeah, that's a good question. So I think for tree-based methods, for this one, It can be used for horizontal and vertical data partitioning if you think about the idea of random forest, say. Because everyone currently, what we get at the global level is really a forest, although it's not that random forest, because it's based on each client's local data. It's more like a fixed forest, random fixed forest rather than random forest. And if we say, think about this, random forest, we can have subsampling. We usually have subsampling both on data level and on feature level. So when we do that, we randomly sample a portion of the whole data set. Now it's equivalent to the horizontal case, split case. And then for the random forest, we also inject the subsampling on the feature space, and that's gonna be equivalent to the vertical data partitioning. So in this case, I think the tree-based methods can also be applied to vertical data partitioning. But the thing is, I'm not sure how, if the vertical data partitioning is split to too many clients, what the performance will be end up. Because usually for random forest, let's say usually we use a subsample rate, say 80% of the feature to build a tree. But in the federated learning case, let's say we have 20 clients, then each client will have a feature space that is a lot smaller than the centralized training. For horizontal split, because the data size can be huge. Let's say we have in total, we have 11 million lines, and even if we split to 20 clients, each client still have a very decent number of training samples. But if we split vertically, then one issue I can think of is that each client will no longer have sufficient features for them to train a good tree on. So that is one potential issue I can think of. But as for the tree-based method itself, it can also work with vertical data partitioning if those partitioning can still give each client a decent number of features to train on, and the trees will be able to achieve a good model in that sense. Yeah.
Yeah. I guess another complication in the vertical case is I think in most real world cases, you wouldn't have the labels for all the workers. Imagine in the medical case, right? The probably hospital has a diagnosis result, but it's not shared with.
Exactly. Usually we assume that only one of the clients gonna hold the labels for the training. Yeah, that's another issue. Yeah, definitely. So in that case, the tree-based method will, the current tree-based method will not work for the vertical split case.
Yeah, for the histogram, I mentioned I'm currently working on the vertical histogram-based federated learning. I think one of the the biggest challenges to deal with label being only available on, say, the first participant, right? So you have to jump through some hoops to enable to share the gradients and even to calculate the gradient, right? Yeah, so it's a pretty big challenge for vertical federated learning. In some cases, you can share the labels. So in those situations, you can also do the tree-based method. But I just don't know what kind of a percentage. It depends on your use case. That's probably the.
Yeah, for vertical learning, not particular for the XGBoost, but you have to consider which portion of the user is matching to the other side of the label the user have. You have to do a user ID match. So in Flare, we do the PSI using PSI protocol to match the user. We have one examples for split learning. So one side has the, one side has the only label, the other one has the training data. So you can sending the embeddings, back and forth. So if you look at NVFlare's GitHub repo has split learning examples there. Little sidetrack on the vertical learning side. Okay, let me there's two more questions. I think one for each author, each speaker. The first one is for Ron. I said, in terms of histogram-based federal learning XGBoost, could we ever perform better than the centralized setup?
So like I mentioned, I think the approach is basically lossless, right? Well, there's some, the way you add up floating point numbers, there's some minor differences, but in terms from sort of the algorithms level, it's basically essentially the same as distributed learning. Would it ever perform better? Yeah, I guess one argument is in the scenario when you cannot share the data, right? So you cannot really do distributed training on the whole data set. But with federated learning, so it gives you more options to train on a bigger data set. So in that sense, it could perform better. But if you have the same data set, like say if you're using the Higgs data set and you split it and you compare the distributed learning result versus the federated learning result, they should be exactly the same. That's our goal anyway. So you shouldn't see any difference in terms of model performance.
So the next question is a follow-up for that question, but I think it's for Ziyu. He said for that question, so my understanding is the performance you reported is just one case federal model better than the centralized model, correct?
Yeah, exactly. Yeah, it's just our approach on one data set we used to showcase this application. And is that the observation that is the federated model can be better than a centralized model is just on that one single example case. It's I guess it will not happen every time, but yeah, we can do experiments with that.
Okay, with that, I would like to thank all the. Oh, there's one more. No. So what's the data set called? That's a Higgs data set. Yeah. So I would like to thank the two speakers, Ron and Ziyu, for their insightful and deep thoughts on the XGBoost. They're the experts on those areas. I also want to kind of pull a plug here. So we literally just released the NVFlare 2.3.0 last week, April 6th, just a few days ago, and it has a tons of features and examples. Take a look there, and you might find something